Alright, 7-6 operations with radical expressions. This is our last section of chapter 7. We're going to pull together the skills we learned last week and actually perform some operations with some of these radicands. Alright, so adding and subtraction expressions with like radicands. Alright, it's like terms. Alright, these are considered like terms, and then you just combine your like terms. So you've got the square root of x plus the square root of x. Remember, there's an invisible 1 here in front of each of these radicals. This would equal 2 the square root of x, because you have 2 square roots of x. Alright, so that's what we're doing. These are the easiest of them. Alright, either you're adding or subtracting, so we'll take that number that's out in front, so 3 plus 7, we'll group those together, and our like term, the square root of 7. Well, 3 plus 7 is 10, the square root of 7. Okay? So, the only one we were having issues with for these, with the assignment, was the invisible 1. So you do some math on one of them, you end up with maybe a negative 1. You keep the negative and you make that 1 invisible. Alright? So don't stress out when it tells you it's wrong and you're like, I've done the math 5 times. Just make the 1 invisible that's in front of the radical. Alright, but don't lose the negativity. And yes, you can have a negative sign outside of the radical. That's perfectly fine. Alright, let's move on. Let's add and subtract expressions with unlike radicands. Alright, so the cube root of 40 and the cube root of 135, these are not like terms. And these are not all simplified either. So the first thing we're going to do is we're going to work on simplifying, having the smallest number we can under that radical. That comes in our prime factorization trees. So let's see, the smallest obvious is 2, 20, smallest obvious 2, 10, and 10 breaks down into 2 and 5. Now because it's cube root, what we're trying to pull out is groups of 3, okay? So I have a group of 3 2's. I can pull out a 2. So I started with this 6 out here. Multiply it by cube root of 2 times 2 times 2 is 2, so we pull out that 2. And what is left under the cube root? 5. Well, 6 times 2 is 12, the cube root of 5. Alright, don't forget we're subtracting. Now let's check out this one. Alright, the lowest obvious number is 5. Okay, and 5 times 27. The lowest out of 27 is 3 times 9, and 9 breaks up into 3 and 3. Again, because we have the cube root of, we are looking for groups of 3. So I have one group of 3 3's. So I can pull out 3 from under the radical. So I have got 2 is already out here, times the 3 I'm pulling out, and what is left under my radical is the 5. Alright, 2 times 3 is 6, the cube root of 5. Now we have like terms, alright, and now that we have like terms, we can math. Alright, so this is 12 minus 6, cube root of 5, and that would be 6, the cube root of 5. Alright. For the most part, we really have gotten into a good groove with these prime factorization trees. doing really good with these in class, so I'm really pleased with the progress on these. All right, let's flip these over and let's talk about a real world application and multiplication, and how multiplication is different, we aren't combining like terms like we are with addition and subtraction, okay? So we treat multiplication a little differently. All right, so first, our real world problem. Use radical expressions. All right, so we have Cade is decorating a rectangular pavilion. All right, so we've got a rectangular pavilion, so I'll just draw that, okay, for a party, and wants to string lights along the edge of the roof, so along the outside edge of the roof. All right, so we have two sides combined, so that means together. They've added them together already. 26 square root of 5 feet. The other two sides have combined, okay, which means they've already been added together, okay. 12 square root of 45 feet. How many feet of lights will Kate need to decorate the entire pavilion? We're trying to go all the way around the pavilion. We've already combined or added these two. We've added these two. And now to get the whole thing, you must add them all together, okay? So we've got 26, the square root of 5, and we're adding 12, the square root of 45. Can we get the square root of 5 any lower? No, we can't. So we're just going to bring that down. But 45 we can. All right. Obviously, I'm going to take out 45 is 5, 9, and then 9 breaks into 3 and 3. Now we're looking for square roots, so we're looking for groups of 2, so we have 2 3s down here, so we can pull that 3 out, okay, and that gives me 12 times 3, and what's left under my radical? Square root of 5, so 12 times 3 is 36, the square root of 5. Now I'll bring my other one down, so 26, the square root of 5. Do I have like terms? Yes, I do now. All right, so we can add these together. So that would be 62, the square root of 5, and we're talking about feet. Okay. So when we're combining things, that's just adding them all together. It's another way of saying adding. All right, so that is what you're looking for when you're adding and subtracting these radicands. You're looking for like terms, and if they aren't like terms, you make them like terms. You got your factor trees, and look to see what you can take out from under the radicand. All right, when we multiply, all right, we're just gonna straight up multiply. What is on the outside? 5 times 4. And we have our square root. And then we just multiply straight up what's on the inside. Okay? So that is 20, the square root of 18. Now once you have multiplied that, okay, is it simplified? Well, the answer is no, it is not. So we can simplify it, and again, prime factorization tree. All right, so we've got 2 times 9, and 9 breaks into 3 and 3. Square root of, we're looking for pairs. We can pull a set of 3 out. Okay? So that gives me 20 times the 3 I pull out, and what is left under my radicand? 2. Remember, whatever you're leaving under the radicand, it's the end of a branch. Okay, it's the end of a branch. So 20 times 3 is 60, the square root of 2. All right. This assignment is actually in McGraw-Hill. All right, make sure you show your work on paper. Good luck.